Hi, let's continue our discussion of control systems by continuing to look at second order systems. In the previous video, what we had done was looked at the response of a second order system and calculated the time response. And now I want to look at that time response in a little bit more detail and look at what kinds of performance measures we can derive from this time response and how we can then design a control system that meets these performance measures. So we have looked at this second order system and we have looked at the output of this second order system which is given here, and you can see that the output is formed of two parts, right? One is the exponential, a decaying exponential, and another is a sine wave. So the sine wave is an oscillatory signal, and the decaying exponential is basically what would happen then to the signal is that your sine wave is going to reduce in amplitude as the time goes by. So there's an oscillation, that oscillation keeps going, but as the oscillation proceeds and as time proceeds, the amplitude of that oscillation keeps going down. So that's what is shown here. So you can see that you have an oscillatory signal, but the amplitude of this signal is going down exponentially over time. And as t becomes infinite, this oscillatory part of the signal becomes zero, and you start reaching the steady state response. Okay. You can also notice that as zeta is usually called the damping ratio of the system. And if the damping ratio of our system is less than 1, you have this oscillatory behavior. But if the damping ratio is greater than 1, you do not have any oscillations. And the response more or less looks like the first order response. And it basically rises and settles down at the final steady state value of 1. Now, this is the transient response of an impulse input, and I will let you calculate that. I hope you did the exercise before this video, and if you had done that, you would have got this output. So let's look at what happens when you vary natural frequency and damping ratio in a particular control system. So the parameter omega n is called the natural frequency. And as you increase the natural frequency, the frequency of oscillation of the signal increases. And you can see that here. So this is omega n equal to 1 radian per second versus the blue trace, which is omega n equal to 10 radians per second. So the oscillations have increased, but so has the uh, exponential drop in the amplitude. Here, the amplitude is dropping much faster than here. And this basically corresponds to the equation that we had before, right? So you can see that the frequency would increase as omega n increases, but also this exponential drop would happen much faster if omega n is higher. Okay, and we have already discussed this. As your damping ratio increases, you have more and more oscillations and you have an overshoot. If you don't have a overshoot, then your oscillations, there are no oscillations, and the signal basically settles down at the final value without going above the steady state value. So what kind of performance measures can you get out of this step response? So the performance measures are shown in this slide. They can be basically divided into two different kinds of performance measures. One is the speed of response. This means how fast does your system respond to the change in input. So the input has changed at time t equal to 0 and it has become 1. Okay, and the rise time and the peak time tell you how fast the system is going to respond. The peak time is basically the time the system takes to reach its peak value, and the rise time is the time it takes to go to a certain percentage of the final value. Okay, sometimes you say 90% rise time, so it reaches zero point 0.9, or you may say 100% rise time, so uh, the first time it reaches the steady state value. So you could use various kinds of measures for that. So those performance measures how fast the system responds. Another kind of performance measure is where you try to measure how close you are to the desired response, right? And these would be measured by things like overshoot. So the overshoot is how far above the final steady state value that you desire have you gone in your output. The settling time tells you how fast you have reached the final value, right? These oscillations can continue for a very long time. And if it continues for a very long time, you have actually not reached your desired response. And the faster you reach the settling time, the faster you're reaching your desired response. So settling time is usually defined as the time that it takes for the output to settle down to a certain ratio of the final output. So here you can see that these blue lines are lines that are drawn at 1 plus delta and 1 minus delta. So what is the time it takes for the signal to settle down between 1 plus delta and 1 minus delta, where delta could be 2%, 5%, sometimes 10% as well. So that's the settling time. Now we can evaluate each of these parameters as shown here on the screen. These formulae are fairly, um, what should I say, standard, and you can evaluate them yourself if you want to. All these formulae are exact except for the rise time, which is basically an approximation. So the rise time actually is this solid blue line, but sometimes we just want to approximate the rise time, and we can approximate it as a straight line as shown here on the figure. So we have all these performance measures, and what we want to do then is to play off one performance measure against the other. What I mean is this. Now, what you can do is you can say, well, I do not want any overshoot in my control system. I want to keep the overshoot to 0. And you can do that, right? Your maximum overshoot can become 0 if you choose your damping ratio greater than 1. But what is the what is the problem associated with it? The problem associated with it is that if you reduce your maximum overshoot, your peak time is going to go up. So, and your settling time is going to go, uh, actually, your settling time becomes less, but your rise time increases. Okay, so the speed of response of your system decreases. So, as you increase your damping ratio, your system responds more slowly. So basically, it's not enough to just take one of these parameters and say, I want to reduce it, because there are effects on the other parameters that you may not like. So take a look at this. So you may want to reduce your overshoot, and to do that, you have to increase your damping ratio. But as you increase your damping ratio, what happens to the peak time? It's increasing, and that is your system is becoming more and more slow. So uh, what we want to actually do is control the overshoot while keeping an eye on the peak time or the speed of response of your system. You want to look at both these parameters in unison and get to a place where you can have the lowest possible overshoot at the speed that you can tolerate for your system, right? So probably you say, well, I can tolerate around about 40% peak overshoot, nothing more than that. And then you say, okay, and the reason why I cannot go below that is because my system becomes too slow at that point. So then you choose, let's say, a damping ratio of 0.3. So you have a certain speed of response, and you compromise. You get a slower response, but you are also keeping an eye on the overshoot, right? So you don't you sorry, let me say that again. So you want the overshoot to become as small as possible, but you don't want the system to become very, very slow. So you try to compromise between these two.